Welcome to MET 1010 Chapter 9 lecture, this chapter on weather forecasting, and we will start with the acquisition of weather information, take a look at weather forecasting tools, then weather forecasting methods, and then weather forecasting using surface charts in conjunction with your upper level charts.
So weather forecasting basically is about predicting how the present state of the atmosphere will change. So creating a weather forecast or forecasting the weather just means first understanding what's happening in the present state, what's happening right now, and analysis of the current conditions of the atmosphere, and then forecasting how those current conditions will change. So in order to accomplish that, you have to know what the present weather conditions are, but not just for where you are. You have to know them for a very large area. And in a real world scenario, the best forecast can only come if you understand what's happening in the present state of the atmosphere across the entire globe. Now, how do we get that information? There's a massive network of weather observing stations, land-based stations, ships, and buoys. They all provide information multiple times a day, forward to maybe even as much as hourly or quarter hourly. Of course, airports have those observations as well. We get upper-level information supplied by radiosondes, which are just instruments tied to weather balloons. Aircraft and satellites give us all that. And then all that information is taken by the World Meteorological Organization, and they ensure the exchange of weather data between their member countries, making sure that all of that data is in the same form. And then, in the United States at least, the National Centers for Environmental Prediction assimilates global data, analyzes it, and runs the forecast.
The number of tools and the complexity of the tools used in weather forecasting is growing every day, but there is a basic group of tools that we use for weather forecasting, starting with high-speed data modeling systems, so your basic weather models, but those weather models can't be run without information, without that analysis, without the weather observations. We have Doppler radar we use for nowcasting. We have metograms that we use for short-term forecasting. We have soundings and upper air wind profiling that we use to help produce upper-level analysis and forecasts, satellite imagery for upper-level analysis and forecasts, and also for nowcasting, and of course then those forecast models. So we want to talk first about forecast models because much of the other data that we use for forecasting is derived from some type of numerical weather prediction or a numerical weather model. So numerical weather prediction, NWP, uses the power of computers to make forecasts. Complex programs provide predictions on atmospheric variables such as temperature, pressure, wind, and moisture. And of course, one of the very first computers in the world was built for the specific purpose of performing weather forecasts. So numerical weather prediction uses mathematical equations for daily weather forecasting. The final chart, when all the information is input, all the weather observations are input, is known as the analysis. And we've looked at a lot of surface and upper level analysis over the last couple of weeks. The state of the atmosphere right now, that is the analysis. Atmospheric models can describe the present state of the atmosphere with mathematical equations. And running those mathematical equations provides us with the forecast. And so the prognostic chart is the final forecast chart representing the atmosphere at a specific future time. Now, just a 24-hour forecast for the Northern Hemisphere requires millions of calculations, and that is why the power of numerical weather prediction did not come into its infancy until the first computers were built, because without a way to do those computations, we couldn't have these weather forecasts. And so the computing power of the data crunching system, and then also the number of data points that you can provide, the resolution of those data points, has a massive impact on just how good your weather prediction, your forecasts are. So that resolution is simply the distance between grid points, or the distance between observation points that are used. There are 4 steps to the running of numerical weather prediction, and these 4 steps are a simplification. Each step involves millions of computations and calculations, but essentially the 4 steps are the analysis, the initialization, the prediction, and the post-processing. So analysis is essentially taking all the input data, all the weather observations from many, many sources, and then providing an analyzation or an analysis of the state of the atmosphere. And that state of the atmosphere is described as a fluid, and gases are in fact fluids, and so the state of the atmosphere is described as a fluid, and as you know, that initial chart is your analysis. The initialization is the process of entering those observations, that data into the model to generate those initial conditions, and it's called initialization. That's preparing the data for input into the model to create a consistent data set. So one, you're going to get different types of data from different parts of the world, but it all has to be brought into one consistent data set. So before you can actually run the prediction of the model, the prediction part of the model, everything has to be in these consistent sets so they can be input easily into the different weather prediction equations. So the prediction or the running of the model in time steps with that sample state of the atmosphere at a given time, the analysis, and then using the equations of fluid dynamics and thermodynamics, we can estimate the state of the atmosphere at some time in the future. And the model is run in time steps, perhaps a 2-minute time step or a 60-second time step, where the analysis is the current state, the time step is the future state, and once that first set of calculations is completed, then that first time step becomes the initial set of observations, and that's how the next time step is completed. So as you go out, which each subsequent time step, that data becomes the new observation data for the calculation of the equations. And what that tells us is that if a weather model begins to go wrong in any parameter, it just gets worse and worse and worse with time. So weather models can diverge rapidly with time if there's bad data in the beginning. Post-processing is the task of removing any biases that particular computer models have, including local effects to create that graphical representation of the analysis and the progs, as well as MOS, which is a model output statistics, basically just the actual numbers of the model output. As good as weather models are in the prediction of weather, providing forecasts in the very short term, or the 6 to 8 hour term time frame, or the 2 or 3 day time frame, or even 6 to 8 days out, or maybe several weeks out, these models have been very effective, and they are still flawed. They are still not precise, and the main reason why they are flawed is because the equations used to model and simulate the atmosphere just cannot be as precise as what's actually happening in the atmosphere. So a couple of things to consider. The models essentially create an inadequate representation of the physical processes of the atmosphere. Not only just the physical processes of the atmosphere, the models can't adequately resolve some surface atmosphere interactions. They can't resolve those micro-scale interactions, and so there's an inadequate representation. Weather processes can be too small or too complex to actually be effectively included in the weather models. So parameterization is the way in which we try and represent all those very micro processes or complex processes and to relate them to the variables on the scales that the model can resolve. So parameterization is this concept of taking all of those things that models can't quite understand and putting them into variables that the models can understand and use. And parameterization is almost always inadequate due to lack of resolution or lack of data, and will ultimately flaw the output. Weather models also have to make assumptions, and it's not that the assumptions are wrong, they're just not completely correct. You can't make an absolute perfect assumption on how the surface and the atmosphere will interact with the processes of the atmosphere. So those basic assumptions can be wrong, or they cannot adequately interpret the influence of microscale processes or surface influences, and that's a flaw in numerical weather prediction. And there's also always going to be some error in initial observation. And as I was explaining with the time steps, the initial observation becomes the first time step, the first forecast. That first time step or first forecast then becomes the initial observations for the next time step. So if observations are wrong, then you're going to have a rapidly decreasing value of a model. So errors in initial observations is a big problem. And then models have inadequate model resolution. Most models are done with grid spacing, others are done with waves, but in the end, you have an observation from, let's say, Orlando Executive, and then MCO, the international airport, maybe out at Sanford, maybe out at Apopka. But those observations, as close as they are together, aren't really quite close enough to give the type of resolution that a model would need to be absolutely accurate. The general methods for trying to increase or improve model forecast accuracy is increasing those initial observations, getting a finer resolution of observations, whether it's at the surface or in the upper levels of the atmosphere, and then fine-tuning and creating more equations to describe what's happening in the atmosphere. And lastly, because there's more equations and more data, increasing computing power. Now, one of the methods that we use to fine-tune models now is referred to as ensemble forecasting. So chaos theory tells us that weather forecasts are going to be highly sensitive to subtle changes in our ability to literally observe what's happening in the weather. So since it's effectively impossible to observe the weather at all places and at all times, weather forecasts are never going to be perfect. So the idea of ensemble forecasting is to improve model forecasting by running several models, or sometimes dozens, with either slightly different initial conditions or by using the same initial conditions but by running slightly different versions of the same model. And what you get is this model output where there's a bunch of different forecast observations or forecast output, and you look at these different forecast output and you decide where the model has a lot of consistency, it's probably absolutely right. Where it's not as consistent, maybe not as right, and you get some averages or means to get a better idea of what's actually going to happen with the forecast. And of course this to the right is showing us an ensemble forecast, and you can see that over Western North America you have a real pretty decent agreement on all the models that there's going to be a ridge of high pressure there. But look to the west out over the Pacific Ocean. You see lots of squiggly lines going everywhere. And probably the reason for that is that there in the eastern Pacific south of the Aleutians in Alaska, there's just not as many observation points. There's not as many data, not as much ship data. So without an adequate number of observations, that part of the model may not be as accurate. And then you can see where different parts of the model are very, very accurate. Over central North America, the northern plains, very tight clustering of the model output. And again, lots and lots of data points to work with. So ensemble forecasting improves model forecasting by running several different types of models with either different initial conditions or slightly different model parameterization. Here is an ensemble model forecast for Boston back in 2013. Each of those colored lines is a different output from the same model, either slightly different initial conditions or slightly different model equations. And the more agreement there is between the different versions of the model, the better the forecast. And this one's showing a pretty wide variation from 3.5 inches of snowfall up to 51 inches of snowfall. So the mean there around 24 is probably closer to what may actually happen, but we don't have a lot of ultimately don't have a lot of agreement. If you look at the model forecast for February 8th from 7 o'clock in the morning to 1 o'clock in the afternoon, there's really good agreement there, somewhere less than 5 inches of snowfall. So snow is definitely a good probability on February 8th, but as the model goes out in time, you can see how widely divergent it is in this particular model. And so again, models tend to get worse the further in time you go. Other weather forecasting tools, again, we had a pretty decent list of them. We talked about Doppler radar, metagram, soundings, satellites. So Doppler radar we've talked about before. Using Doppler radar is a way to do nowcasting. Doppler radar is going to give you an idea of what's happening over the next couple of hours, maybe 8 to 12 hours. So Doppler radar we've talked about, you can see precipitation, and that's known as reflectivity when the model, the radar that is just listens to what's being reflected back to it and giving you an idea of where the rain is falling. There's the Doppler aspect of Doppler radar giving us not reflectivity but velocity, or where the winds are moving and what speed they're moving at, to give us an idea of whether we have rotating thunderstorms or where the winds are moving. And then a new technology with radar is known as dual pole radar. And when they have dual polarization, essentially the radar beam is being sent out in the lateral and then so it's being sent out up and down and side to side essentially. And that dual polarization gives us a much better idea of what type of precipitation is falling. And so here's an example from Wichita of the type of precipitation: hail with rain with the red, heavy rain, large raindrops, and then you can see where you might have snow or wet snow. But that's what dual polarization provides us. But Doppler radar is a great forecasting tool, but only in those short-term nowcasts. These are metograms, essentially using model output statistics or actual numbers coming from the models, not graphs, to give you the variables or the conditions in the future. This is from November 19th to November 21st. And at the very bottom, you have mean sea level pressure. So we see that for a while, the pressure is falling, which means possibly foul weather, and then pressure begins to rise there on November 21st, improving weather. We can see the dew point and the temperature, how they're pretty close together as that the pressure is falling, which means humid atmosphere, better chance for clouds and precipitation. And then as that pressure begins to rise, you get more of a dew point depression. They're further apart, and relative humidity will therefore be lower. We also see that the temperatures are nice and warm, but as that higher pressure builds in at the 850 millibar level, so just off the surface, temperatures begin to fall. We also see the thickness of the atmosphere. So 500 millibar thickness refers to the heights, and so we have high heights with a warmer atmosphere, and with high pressure aloft because of a warmer atmosphere, we tend to have low pressure at the surface, and then as those heights begin to drop as we move into November 21st, a little convergence in the upper levels, forcing higher pressure at the surface. And we see where we have our precipitation, best chance for precipitation, where we have a combination of the low pressure and the high dew point and temperatures, a nice warm atmosphere. So that's a medogram. They're available for every station plot, and they can go out just a couple hours or several days. In order to get initial observations of what's happening above the surface, you have to have something up there to get those observations. Now, aircraft can do that, and we have a lot of aircraft observations, but at every forecast observation point, so every station in North America launches a weather balloon twice a day. And those weather balloons, as old school as they are, give us the data from the very surface right on up to the upper levels of the atmosphere. And that data, as it comes back, is called a sounding. So basically, the weather balloon has an instrument below it that gives us a pressure and temperature and relative humidity. And then it has a radio transmitter that transmits that back. And then as the radio transmitter moves downstream with the winds, it also can tell it's a location, and then by knowing the location with time, we know how those winds are moving in the middle and upper levels of the atmosphere. So a sounding is a vertical profile of the atmosphere depicting temperature and dew point and winds, and you can see, and this is a kind of a straightforward sounding, and why I say that is because the X and the Y axis are parallel, with temperature on the X-axis and pressure dropping from 1,000 millibars at the surface to the 300 millibar level, almost the top of the atmosphere. On the right, you can see the little wind barbs, so we know that in the lowest levels of the atmosphere, our winds are easterly, and then pretty quickly as you go up, those winds tend to turn to the south, and then eventually to the southwest and to the west. And you can see that as you get higher in the atmosphere, those winds also pick up, which is typical above the frictional force of the planetary boundary layer. And then the other part of the sounding shows our air temperature and dew point. And what we see is at the surface, there's a pretty close, the dew point and the temperature are fairly close. So there's a small dew point depression, so that's a fairly high relative humidity. And then just above the surface, they diverge, and the dew point goes down and the temperature goes up. So there's a big dew point depression in that 925 to 900 millibar level. And so that means there's some fairly dry air up there. Then you can see how the atmosphere kind of moistens up as you go higher, then dries out again. And that's the sounding gives us a short-term sort of mesoscale forecast. So this is really for where this sounding was taken, and then sort of in the next 6 to 8 to 12 hours. It gives us some meteorological indexes that we use for short-term forecasting as well. And if you click on the on the link, it's going to take you to the Unisys weather page, and it's going to show you where you can get soundings from all over the country, and those soundings we'll talk more about in class.
This is one more tool used in assimilating current weather data, the analysis of the atmosphere. This is a wind profiler, a very sensitive radar system that essentially can detect wind speeds and directions to a height of about 16 kilometers. So very, very highly sensitive, and giving us an idea of how the winds are moving and turning and their speeds through a very deep layer of the atmosphere.
Satellite imagery is going to do two things for us: short-term forecast through, let's say, 1 to 2 day forecast, looking at cloud patterns on the globe. But satellite imagery also helps us out with getting initial observations for middle and upper level winds and humidity levels, water vapor, and wind speeds and wind directions. So satellites have a couple different functions, and we have two basic types of satellites: the geosynchronous satellites, or geostationary satellites, and then polar satellites. So the geostationary satellites, known as GOES, or the geosynchronous operational environmental satellite, they are at an elevation, 36,000 kilometers or 22,300 miles. They're at an elevation that they are in geosynchronous orbit. So they're right above whatever level we want them above, and they stay right over that level. So the geosynchronous, the GOES satellite that's over eastern parts of North America and then western parts of North America, they are in a geosynchronous orbit, so they orbit right along with the planet. And they orbit at the same, so the speed that they're going keeps us right aligned with the planet. So they're always taking pictures of the same area. They're taking continuous pictures of the same region. Whereas the polar satellites, they are at a much, much lower altitude, about 530 miles above the Earth. And they zip along pretty quickly, making several trips around the Earth every day. And as they make those trips, you can see that the Earth then rotates beneath them. So one stripe, narrow stripes, and one trip around the Earth, and as the Earth rotates by, they're a couple thousand miles to the west, they get another stripe. And so these polar orbiting satellites give us a much, much more detailed look at what's happening on the Earth's surface. And we can see polar satellites by clicking on this link, and we'll do that in class and give you an idea of what those satellite images look like. The geostationary operational environmental satellite is GOES, so it detects two things: emitted and reflected radiation with the sounder and the imager. And the sounder detects emitted radiation, and the imager detects reflected radiation. Now, the reflected radiation, or the imager, is basically just a big digital camera in space. Imagine being 22,000 miles up, you're in the space shuttle, you look down, you take a picture with your cell phone, and that's going to be the image that we get from the imager, that reflected radiation, and those are known as visible satellite images. The other radiation we get is going to be emitted. What's emitted from the Earth? And what's emitted from the Earth is going to be long-wave radiation, so it's going to be infrared. So the GOES satellite either gives us infrared or visible images. The infrared images detecting the heat coming up off the Earth, and we can tell whether those are clouds or that's the Earth itself. And then the second thing that the sounder can detect, the second type of emitted radiation, involves water vapor. So the GOES satellites can give us infrared or water vapor imagery based on emitted radiation in the sounder, and then visible satellite imagery based on reflected radiation from the imager. Infrared images, the sounder detects emitted radiation in the form of heat. So where it's very, very cold, that's going to be the tops of very, very high clouds, and they're typically painted bright white. And then if you have low clouds, you're going to have warmer cloud tops. And so they're radiating away or emitted infrared radiation, as all objects do, so clouds do it as well. And those low clouds are going to be warmer, and they're going to be painted as gray. And so on an infrared satellite image, you're basically looking at whether it's bright white or gray as how high the clouds actually are. It doesn't really give you an idea of thickness or whether there's precipitation, but how high the clouds are. And we know that lower clouds can produce certain types of weather, and high clouds other types of weather. Water vapor images, also the sounder detects emitted radiation, but it's detecting emitted radiation depicting water vapor. And this is only in the middle and upper levels of the atmosphere. It does not depict the amount of moisture at the surface. So it's not the way we know what the humidity is at the surface. That's done with observations. But water vapor in the middle and upper levels of the atmosphere, and how that water vapor moves in the middle and upper levels of the atmosphere is a very good indication on what's happening with the mid and upper level winds. And then lastly, the visible images, that's reflected. That's the imager sees visible light reflected from objects. And so thick clouds are going to have what we call deep optical depth. They reflect more light back, so they're going to be pretty bright white. And then thinner clouds are going to be more gray. But again, this doesn't show us the level of those clouds, just how thick they are. So you have to use all three of these different images together in order to get a solid understanding of what's happening with the satellite image. And here you see three different images, three different satellite images, same time, same region, visible, infrared, and water vapor. The visible, again, because you can see a depth or how thick the clouds are, and you can also see, literally see what's being reflected back, you not only get the cloud height by their thickness, but you also see shadows. So if you look at this line stretching from the Great Lakes, really the eastern Great Lakes, down into western parts of Ohio and then into central Kentucky and into Tennessee, and you can see all that texture. That's literally the texture of the thunderstorms, where the high tops of the thunderstorms are casting shadows on the clouds out ahead of them, and you can actually get that texture. And you also see some of that texture down in parts of Alabama and Mississippi. Looking at the infrared satellite in the same region, we see those bright clouds, meaning those are very, very high clouds. And then looking at the water vapor imagery, we can see along that same line, that's where our moisture is, where on the back side of that line is very, very dry. So what we're looking at here is a very typical mid-latitude cyclone, where the low is somewhere over Wisconsin with the counterclockwise turning that you can see very well defined in the water vapor imagery, and then the cold front extending out across the Great Lakes, down across the Ohio Valley, and into the Gulf of Mexico. And along that cold front, you can see with the visible satellite imagery that texture giving us the indication that there we'll find thunderstorms. Putting the observations together from the surface, the low levels, the mid, and the upper levels of the atmosphere, whether it's from surface observations or from sounders or wind profilers or from airplane observations or from observations made by satellite imagery, and then using our numerical weather prediction, we can provide ourselves not only analysis charts, but also prognostic charts, known as progs. In this case, what we're looking at is 4 24-hour progs from North America. We do not have a surface prog here. What we do have is an 850 millibar, a 700 millibar, a 500 millibar, and then a 300 millibar. So that 850 millibar chart is a pretty good indication of what's happening at the surface. It's only about 1,500 meters up off the surface, with an area of low pressure essentially moving out of the mid-Atlantic into the New England states. It looks like it's just south of Pennsylvania, and there's a lot of humidity associated with this, and pretty decent wind speeds associated with that low. And then as you go up in the atmosphere, you start to get the 700 millibar chart. That low is a little bit further displaced back to the west, and then further up in the atmosphere, the 500 millibar chart. So at 500 millibars, you're beginning to talk about the upper levels of the atmosphere. That 500 millibar level is everything below that, middle and surface. Everything above it's going to be the upper levels of the atmosphere. And there you see your long waves in the westerlies, with a big trough of low pressure over the eastern half of the country, and a ridge of high pressure kind of over the Intermountain region and the Rocky Mountains. And then that 300 millibar chart, there you see what's happening in the upper levels. And so you're looking at wind speeds. And so those are your jet cores. That's your jet stream and your jet cores moving through the upper levels, the jet streams. And so you use all these different charts to tie together to get an idea of what's happening with the weather. And here's a pretty good indication of how you're going to use those charts. And we've looked at lots and lots of surface maps, and we know that's where you find the location of frontal systems, highs and low pressures. We can determine where the isobars across the winds, indicating strengthening or weakening low pressure. We can see warm and moist air that may give us a shower and thunderstorm development. At that 850 millibar level, we can see where high moisture values are coming in to produce heavier precipitation. We can see what's called the low-level jet that may be feeding moisture into thunderstorm development. Once we start getting up closer to 10,000 feet, or that 750 millibar or 700 millibar level, again, moisture. We can also see temperature advection at that level, where cold air is moving in to strengthen or weaken frontal boundaries. At 500 millibars, now we're talking about the general steering level for mid-latitude cyclones, also for hurricanes and tropical cyclones. The 500 millibar level gives us the long waves in the westerlies, locations of ridges and troughs, but also short waves that help to generate and strengthen the surface features. And then once we get up to the 300 millibar level, you can see that's the location of your jet stream and your jet streaks. With all this data brought together, whether it's your observations and your analysis or your prognostic charts, your progs for 12, 24, 36, 48 hours, the types of weather forecasts that we can create vary from very short range or nowcasts all the way down to seasonal forecasts. So those nowcasts, not more than 6 hours. So that's where you can be using your radar, maybe your satellite imagery, maybe your soundings and some of your meteorological indices. Short-range forecasts, so 6 to 60 hours, up to 2.5 days. That's going to be using what's happening in the 500 millibar levels and helping to sort of forecast out your surface chart. So your medium range is going to be up to 8.5 days, definitely what's happening in the long waves of the westerlies, similar to your long-range forecast at 8 to 16 days, and then seasonal forecast, which is really just a summary of trends, but seasonal forecasts will also begin to pull in what's happening with those teleconnections, those sea surface atmosphere interactions that actually help to change weather over different parts of the world. And we do want to note that those long-range forecasts are less specific than our short-range forecasts. So our nowcasts can be very, very accurate, where our short-range forecast can be great, up to about 1.5 to 2.5 days. And then as you start to talk about the medium range and certainly the longer range forecast, you get much lower accuracy in the forecasts. But it's a flip-flop, because if you're trying to forecast a very small event, what's the temperature going to be in Altamont Springs in 15 days? That's going to be very difficult to hit on the head. But if you're forecasting a very large event, like will there be a major tropical cyclone, or will there be a big trough in the upper levels of the atmosphere, that'll be much easier to predict in those longer ranges. A quick sidebar as to the nomenclature surrounding some of our short-term forecasts, or even those nowcasts, watches and warnings. And your watches basically come in those short-term forecasts that up to 2.5 days, and your warnings are more of your nowcasts. So a watch is when atmospheric conditions favor hazardous weather occurring over a particular region over a specific time. So a tornado watch might be in effect from 10 o'clock this morning until 12 o'clock tonight for a region, because the atmosphere in that region during the afternoon and evening hours is going to be prime for creating tornadoes. And so a watch is going to be somewhere in that nowcast, a short-term forecast. And then sometimes they may go out a little bit further than 2.5 days if you're talking about very large features that we can see in the westerlies. Now, warnings are much more typical as being nowcast. There is a tornado warning in place, meaning there's a thunderstorm that very likely is producing a tornado, or there's a severe thunderstorm warning in case, or there's a high surf advisory in place. And so those warnings indicate hazardous weather is either imminent or actually occurring within a particular region. Now, hurricane warnings can go out 24 hours, so they sort of cross that nowcast into short term. But essentially, your watches are going to be a little bit longer range, indicating that atmospheric conditions are favorable for hazardous weather, and your warnings are going to be shorter range, indicating that hazardous weather is imminent or are actually happening. Other types of forecasting methods are available, and many of these not necessarily needing powerful computers. Persistence forecasting is something that works well in Central Florida in the summertime. Persistence forecasting tells us that future weather will very likely be the same as present weather, unless something significant occurs that's going to change it. So we have a very static weather pattern in Central Florida in the summertime, so you're pretty certain on July 1st, when it's hot and humid, with scattered afternoon showers and thunderstorms during the afternoon, that on July 2nd, 3rd, and 4th, it's also going to be hot and humid with scattered afternoon showers and thunderstorms, and that is a persistence forecast. Now, A trend forecast or a steady state forecast is a little bit different. That involves specific weather systems. And for instance, if you have a mid-latitude cyclone, or let's even just say a hurricane that's moving in one direction and one speed, a steady state or a trend forecast will say that hurricane will continue to move in the same direction and at the same speed, and you can forecast the impact of the hurricane in that way. Analog forecasting is simply looking at the pattern, the upper level patterns, the surface patterns, and recognizing when in the past that patterns have been similar, and then determining how those past weather patterns played out and using that to produce a forecast. Statistical weather forecasting gives a statistical chance of a specific weather event based on forecast data. So taking in forecast data, you give a specific chance of a weather event occurring, whereas a probability forecast is more of a statistical chance of a specific weather event occurring based on 30-year averages. So one uses historical averages to determine whether there'll be showers and thunderstorms tomorrow, and the other uses current weather conditions. Statistical forecast uses the current weather conditions to determine what the probability of a specific forecast event will be for the next day or the next week. And then the climatological forecast is simply based on the climatology of a region. If the climatology of Central Florida calls for hot and humid conditions in July, then you can forecast a day in July will very likely be hot and humid. This is an example of how we would use our 500 millibar chart, which is going to be the chart on the bottom right, to give us an indication what's going to happen to these surface features, which is going to be the chart in the upper left. So starting with the 500 millibar chart, pretty simple. We have a ridge of high pressure over the west coast, and essentially a ridge of high pressure over the western Atlantic. And right there, smack dab in the center of the country, we have our trough of low pressure in the upper levels of the atmosphere. The upper level low is the L in purple, and that is in the base of that trough. And you can see in the base of that trough that winds are converging in the upper levels as they enter that trough, in the entrance region of the trough, and in the exit region of the trough, let's say over Missouri and Iowa and Illinois, Indiana, winds are diverging away from themselves. They're speeding up and they're moving away. So our upper level trough is over Nebraska, and if you're using this forecast map, this analysis map, you can pretty safely forecast that there'll be some type of a surface low developing in the exit region of the trough or over northern parts of Kansas, northeastern Kansas, or northwestern parts of Missouri. Now, the upper left is the surface map, which is essentially verifying that forecast with our surface low right in that same region, and just to the south and the east of the upper level low. Now, if you have a surface low with a counterclockwise flow around it, you're very likely going to have a north wind on the north and west side of the low and a south wind on the east and south side of the low. And so you can see where you draw your warm front and your cold front, and you have your complete mid-latitude cyclone. And so that is your upper level chart helping you to determine a forecast for your surface weather system. Now we're going to take a look at how that surface weather system is going to move based on that upper level chart. So we know that our lows and our highs essentially follow the movement of the 500 millibar level, the upper level chart, and about half the wind speed. So we can see that low essentially over, again, northeastern parts of Kansas, northwestern parts of Missouri, is underneath a southwest upper level wind of about 50 knots. So the expectation is that low is going to move at about 25 miles per hour toward the north and east, toward Lake Michigan. And we'll see that on the next chart, how that plays out and how that works. Based on the upper level 500 millibar chart on the previous slide, the expectation that our area of low pressure situated just over northeastern parts of Canada, or Kansas that is, will move off to the north and east at about 25 miles per hour. So we take it out 12 hours, it moves from its current location to Chicago. Another 12 hours, it moves to just north of the state of Ohio. And along with that, the cold front and the warm front are going to move along as well. And you can see that as the cold front and warm front move up to Chicago, they become occluded, and that occlusion deepens through time. High pressure to the north and west of our surface low, it moves to the south and east following the upper level chart, bringing that cold, dry air with it. and the high pressure that was to the east of our surface low, it moves off just north of east on out into the Atlantic Ocean. And on the next slide, what we're going to see is the result of that transition from the low's current position to its furthest east position and how it will play out on the surface weather map at that time frame. What you're looking at here is the surface weather map for the last position of our extratropical cyclone on the previous slides. The previous slide was showing the forecast based on the 500 millibar chart, and the forecast verified that low ends up just to the, it looks like just to the east of Chicago, maybe just to the south and east of Chicago. The isobars indicating the lines of equal pressure at the surface, and you can see the station plots showing a northwest wind and snow north and west of the low in Chicago. And then along the cold front, as we go down into Augusta, Georgia, we have showers and thunderstorms along the frontal boundary, snowfall to the north of the low, and rainfall extending north of that warm front. Pretty typical late stages of a mid-latitude cyclone, and very similar to what we see move across the country during the fall and the wintertime periods here in North America. So this is pretty much the end of the lecture for Chapter 9. We've kind of come full circle. We started out the first day looking at a surface weather map. We wind up looking at a surface weather map. Our next two lectures are going to be on thunderstorms and severe thunderstorms and tornadoes. And then the final lecture will be on tropical cyclones, which includes hurricanes, tropical storms, and tropical depressions.